Okay, so let's look specifically at limits of piecewise functions. So, first example here, we want to know what is the limit as x approaches 1 of g of x. And this time our piecewise function g of x is x plus 1 if x does not equal 1, and 7 if x does equal 1. So, if your conditions for your piecewise function are of the form if x doesn't equal a specific number and then if x does equal that specific number, the way that affects your limit is, remember, the limit is not what is actually happening at that number, it's what's happening as you approach that number. So because we are using x plus 1 for every single x value except 1, that means as I approach 1, I'm going to still be using this x plus 1. Right? Even if I'm really, really close to 1, if I'm at 0.99, I'm still using this x plus 1. It's only that at specifically 1 that I use this other function, which is just a constant. It's 7. So as I approach 1, from both sides of 1, I'm going to be using x plus 1. And this is a case where I can just do direct substitution, which means our limit is 2. If you think about the graph of g of x, what this would be is it would be the line x plus 1, except at 1 you would have an open circle. That open circle would happen at 1, 2. Okay, so we would have at 1, 2 there would be an open circle there. Otherwise we're going to have this straight line coming through here. And then at 1 there's actually a point up here at 1, 7. So that's what g of x would look like. But again, if we're talking about limits, we're saying, what does it look like our y value should be as our x's get closer and closer and closer to 1? You know, if we get closer and closer to 1, it looks like our y value is going to be 2. However, the actual y value is 7. But again, for limit, that doesn't matter. Okay. The next piecewise function that we have is the limit as x approaches 4 of f of x. Now this time our conditions for our piecewise function are a little bit different. They're not if x equals and doesn't equal a number. It's if x is less than a number and if x is greater than a number. So if you want to evaluate a limit of a piecewise function, and the conditions of that piecewise function are use this if x is greater than that number and use this other thing if x is less than that number, what you have to do is you have to split this limit into its from the left and from the right. So it's one-sided limits. Okay? So we're going to look at what happens as I approach 4 from the left of 4 and what happens as I approach 4 from the right of 4. So from the left, that would mean if x is less than 4, right? That means you're going towards 4 from the left side of 4. So which one would that be? That would be the second one in this case, because that's what I'm supposed to use if x is less than 4. So my left-handed limit, I'm going to use this 8 minus 2x. And I can still do direct substitution here, even though it's 4 from the left. I'm still going to use direct substitution as long as I get a defined value. So I'm going to have 8 minus 2 times 4, which is going to be 0. From the right of 4, that would be the top one, right? So if I'm approaching 4 from the right, I'm approaching 4 from a side of where x is greater than 4. And this would be where I would use the square root of x minus 4. I can do direct substitution. I get the square root of 4 minus 4, which would be 0. Now, in order for this limit to exist, my left and right hand limits have to give me the same value. And they do. Therefore, the answer to this limit is 0. If your left and right hand limits do not give you the same value, then this limit does not exist. Okay, so we have to get the same thing from both of these. The very last thing on here is just a theorem that says if we have two functions where one is always less than or equal to the other one, then the limit as x approaches that number of each one of those functions will fall in that same order. That the function that's always less than the other one, its limit will also be less than or equal to the limit as x approaches a of that second function. Okay, so just a small theorem there. That we'll look at some examples to make sense of that.